In 1913, Niels Bohr proposed an atomic model that quantitatively explained the features of the structure of hydrogen atom and its spectrum. The postulates of it describe motion of electrons in a stationary orbit, fixed energy of electrons, energy change during transition of electrons, and fixed angular momentum of electrons. The first postulate states that the electron in the hydrogen atom can move around the nucleus in circular paths of fixed radius and energy called orbits. Orbits are arranged concentrically around the nucleus and are also called stationary states or allowed energy states. Electrons are held by the nucleus in orbits by a strong electrostatic force. According to the second postulate, the energy of an electron in the orbit remains constant until the electron absorbs energy to jump to a higher orbit, or releases energy to move to a lower orbit. So each emission or absorption of radiation energy represents the electron transition from one stationary orbit to another. The energy difference between the two orbits is given by equation delta E is equal to E final minus E initial. The third postulate states that the frequency of the radiation emitted or absorbed can be represented by the equation nu is equal to delta E divided by H. That is, E2 minus E1 divided by H, where E1 and E2 are the energies of the lower and higher stationary states, and H is the Planck's constant. The fourth postulate states that an electron moving in a circular orbit has an angular momentum equal to the product of its mass me, linear velocity v, and radius of orbit r, which can be expressed as an integral multiple of h divided by 2 pi, where n is an integer that has the values 1, 2, 3, and so on, and h is the Planck's constant. Since angular momentum can only be an integral multiple of h divided by 2 pi, only certain fixed orbits or stationary states are allowed for electrons to move around the nucleus. Let us now get into more details of Bohr's theory of hydrogen atom. According to Bohr's theory, the stationary states for electron are numbered n is equal to 1, 2, 3, and so on. These integral numbers are called principal quantum numbers. The radii of stationary states or orbits can be given by the expression radius of the nth orbit Rn is equal to n square multiplied by the constant A0, which is equal to 52.9 picometer. This means that the smallest possible value of r, or the radius of the very first orbit, where the sole electron of the hydrogen atom found in its ground state is equal to 52.9 picometer. This radius is called Bohr's radius. The energy of a stationary state or orbit is given by the equation energy of the nth orbit En is equal to minus Rh multiplied by 1 divided by n square, where n is the principal quantum number of the orbit and Rh is Rydberg's constant, whose value is 2.18 multiplied by 10 raised to the power minus 18 joules. Energy of nth orbit of a hydrogen atom in electron volts is equal to minus 13.6 divided by n square. Thus, the energy of the ground state n is equal to 1 for hydrogen atom is equal to minus 2.18 multiplied by 10 raised to the power minus 18 joules. The energies of excited states can be measured in the same way and represented in the form of an energy level diagram. Note that the energy of the stationary state, n equal to infinity, is 0. At this energy level, the electron is completely free from the influence of nucleus. In other words, the hydrogen atom is said to be ionized. An electron emits energy as it approaches towards the nucleus, and hence its energy decreases with decrease in distance between it and the nucleus. This principle accounts for the negative sign of energies of electrons in various orbits. Bohr's theory also applies to other ions which are isoelectronic with hydrogen, such as helium plus, lithium 2 plus, and beryllium 3 plus ions that contain 1 electron each. The energies of the stationary states of hydrogen-like species are given by the expression En is equal to minus Rydberg constant multiplied by the square of atomic number divided by the square of principal quantum number. The orbit radii of these ions is given by the expression Rn equal to Bohr's radius multiplied by the square of principal quantum number divided by the atomic number. From the orbit energies and radii equations of hydrogen-like ions, it can be deduced that with increase in Z, the value of energy becomes more negative and the radius becomes smaller. Bohr's theory also states that the magnitude of velocity of electron increases with increase of positive charge on the nucleus, that is, increase of atomic number, and decreases with increase of principal quantum number. Although Bohr's theory is not based on the modern quantum mechanics, it helps to resolve many questions related with atomic structure and spectra. For example, it provides explanation for main limitation of Rutherford's model, the stability of an atom. According to Bohr's model, electrons are held in stationary orbits by virtue of an electrostatic force. That's why they don't fall into the nucleus. The model also stated that electrons are distributed in concentric orbits around the nucleus. The orbits have a specific energy, which decreases or increases during the electronic transition. In addition, it helps to quantitatively explain the emission and absorption line spectrums of hydrogen and hydrogen-like species. Let's see how. According to the second postulate of Bohr's model, the energy gap between the two orbits is given by the equation delta E equals to E final minus E initial. Since the energy of a stationary state is given by the equation En is equal to minus of Rydberg's constant multiplied by 1 divided by n square, we can substitute E final in the energy change equation by minus RH divided by n final square and E initial by minus RH divided by n initial square to get an equation similar to the expression used by Rydberg. Note that in case of absorption of energy, delta E is positive, and in case of emission, delta E is negative. Thus, each spectral line in absorption or emission spectrum can be associated to transition of states by the electron of a particular hydrogen atom. Bohr's model also shows that the intensity of each spectral line depends upon the frequency or wavelength of photons absorbed or emitted. Because of the presence of multiple hydrogen atoms, a large number of spectral lines are observed. The frequency associated with the absorption and emission of the photon can be calculated using the equation delta E divided by h, where h is the Planck's constant. The wavelength can be calculated by dividing the velocity of electron with the frequency of the radiation. The more the number of photons of a particular frequency or wavelength absorbed or emitted, the more the intensity of the associated spectral line. Bohr's atomic model of hydrogen atom, therefore, helps to get most of the answers to the questions prevalent at that time. However, it could not explain the line spectrum of multi-electron atoms. Presence of doublets in the hydrogen spectrum when observed through sophisticated spectroscopes. The splitting of spectral lines in the presence of magnetic field, a phenomenon called Zeeman effect. The splitting of spectral lines in the presence of electric field, a phenomenon called Stark effect. The ability of atoms to form molecules through chemical bonding. And the dual nature of electrons, both as wave and particle. It contradicts Heisenberg's uncertainty principle, which says that it is possible to determine both the position and velocity of an electron simultaneously and accurately. Two important developments that questioned the rationality of Bohr's model are: 1. Dual behavior of matter, and 2. Heisenberg uncertainty principle. Let's understand these developments in detail. After the dual behavior of electromagnetic radiation was known, de Broglie proposed in 1924 that all matter has wave and particle-like properties. His theory implied that just like photons, every moving object, be it an electron, a ball, or a planet, has a wave nature. He also gave the relation between wavelength and momentum of a material particle based on the energy equations of photons in their wave and particle forms. A photon displaying wave character has energy equal to h multiplied by nu. A photon having a particle character has energy equal to m multiplied by c raised to the power 2. By combining these two equations and replacing nu with c by lambda, we get lambda is equal to h divided by mc. To generalize the equation for any material particle, c, the velocity of light is replaced with v, the velocity of the material particle. The resultant equation is called de Broglie's equation. Since the momentum of a particle is the product of its mass and velocity, the relation between wavelength and momentum of a material particle can be given by de Broglie's equation. It can be noted from de Broglie's equation that the wavelength and mass of an object are inversely proportional. That is, that the wavelength of heavier objects is small and vice versa. Thus, the wavelength of lighter particles like electrons can be measured experimentally, whereas that of heavier objects like a ball or a planet cannot be detected. De Broglie's theory and equation was later proved to be correct when it was found that an electron beam undergoes diffraction, a property that is unique to waves. The wave nature of electron forms the basis of an electron microscope that achieves a magnification of about 15 million times, and is therefore a powerful tool in modern scientific research. Let's now look at the Heisenberg uncertainty principle. In 1927, a German physicist, Werner Heisenberg, took forward the concept of dual behavior of matter and radiation to give a principle about the uncertainties in simultaneous measurements of position and momentum of small particles. He proposed that it is impossible to measure simultaneously and accurately the exact position and momentum of a small particle like an electron. Mathematically, Heisenberg's uncertainty principle can be expressed with the equation delta x multiplied by delta px is greater than or equal to h divided by 4 pi, where delta x is the uncertainty in position and delta px is the uncertainty in the momentum of the particle. This equation can also be expressed in terms of mass and velocity of the particle. Note that the uncertainty in the position and velocity are inversely proportional to each other. This means that if the position of the electron is known with high degree of accuracy, then the velocity of the electron will be uncertain and vice versa. Also note that the uncertainty in the position and velocity are inversely proportional to the mass of the object. That is, uncertainty in the position and velocity decreases as the mass of the object increases and vice versa. For example, if the uncertainty principle is applied to a macroscopic object, an object weighing a milligram 10 to the power 6 kg, the value of the product of delta V and delta X is extremely small. Therefore, the associated uncertainty is also insignificant. On applying this uncertainty principle to a microscopic particle, like an electron having mass equal to 9.1 multiplied by 10 to the power minus 31, we find that the product of delta V and delta X is significant enough and therefore cannot be ignored. Hence, we see that Heisenberg's uncertainty principle also holds significance only for motion of microscopic particles and not for macroscopic objects. The position of an electron can be determined experimentally by illuminating it with electromagnetic radiation having a wavelength smaller than the dimensions of an electron. However, the velocity of an illuminated electron cannot be detected as the high momentum photons of the light increase the energy of electrons by collisions. As we have already calculated that for an electron, the product of delta X and delta V is found to be equal to 10 raised to the power minus 4 square meters per second. Therefore, the uncertainty in velocity can be calculated by substituting the value for delta X, say 10 to the power minus 8 meters, in the Heisenberg's equation. This means that if one tries to find the exact location of the electron to an uncertainty of only 10 to the power minus 8 meters, the uncertainty in velocity becomes positive and enormously significant. This value of uncertainty in velocity is so big that the classical picture of electrons moving in Bohr's orbits becomes unrealistic. As it is impossible to determine simultaneously and accurately the position and velocity for an electron at any given instant, it is not possible to talk about the trajectory of an electron. Thus, Bohr's model not only ignores dual nature of matter, but also contradicts the Heisenberg's uncertainty principle. Due to these inherent weaknesses in the Bohr's model, a need for such an atomic model arose which could account not only for the dual nature of electrons, but also be consistent with the Heisenberg uncertainty principle. This search led to the advent of quantum mechanics. The de Broglie's dual behavior of matter and Heisenberg's uncertainty principle gave birth to a completely new branch of science called quantum mechanics. Classical mechanics successfully explains the behavior of macroscopic objects, such as falling stone, on the basis of particle nature. It ignores the concept of the dual behavior of matter and thus fails to explain the behavior of microscopic particles, such as protons, electrons, and so on. On the other hand, as quantum mechanics is based on the wave properties of matter, it describes the behavior of microscopic particles in a much better way. Hence, quantum mechanics is a theoretical science that helps to study the motions of the microscopic objects that have observable wave-like and particle-like properties. Quantum mechanics was developed independently by Werner Heisenberg and Erwin Schrödinger in 1926. The fundamental equation in quantum mechanics is Schrödinger's wave equation. In quantum mechanics, the mathematical expression which describes the wave motion associated with a particle is popularly known as Schrödinger wave equation. It gives the probability of finding an electron at different points in an atom. The Schrödinger's wave equation is obtained by differentiating the equation for the standing wave of an electron in the hydrogen atom. In short, Schrödinger wave equation is written in terms of Hamiltonian operator as shown here. In this equation, E stands for total energy of the system, which includes kinetic energies of all the subatomic particles and potential energy due to attractive and repulsive forces operating in an atom. When Schrödinger wave equation is solved for an electron of an atom, such as hydrogen atom, it gives the values of the possible energy levels in which the electron can move, called quantized energy states, as well as the wave functions corresponding to these energy levels. Note that, in quantum mechanics, all the properties of a system are expressed in terms of a wave function. This is obtained by solving the Schrödinger's equation. The wave function, psi, is a mathematical function that represents amplitude of the wave. It does not carry any physical significance. Therefore, the square of the amplitude of electron wave, that is, psi square, gives the probability of finding the electron at a point within an atom. That is why the function psi square is called probability density and is always positive. By finding the probability density at different points in an atom, one can predict the region of space around the nucleus, within which the probability of finding the electron is the maximum. This three-dimensional space around the nucleus, where the probability of finding the electron is maximum, is called orbital. This is why the wave function for an electron in an atom is also called orbital wave function or atomic orbital. An electron can have multiple wave functions and therefore multiple atomic orbitals. Schrödinger wave equation can successfully explain all aspects of hydrogen and hydrogen-like species, It, however, cannot be completely solved for multi-electron atoms. Such calculations show that the orbitals of multi-electron atoms are similar to the orbitals of hydrogen atom in most aspects. The principal difference between the orbitals of single electron atoms and the orbitals of multiple electron atoms is that the orbitals of multi-electron atoms are contracted due to increased nuclear charge. In addition, unlike orbitals of hydrogen or hydrogen-like atoms, whose energies depend only on the principal quantum number, the orbital energies in multi-electron atoms also depend on azimuthal quantum number, in addition to principal quantum number. Let us now move on to certain other important aspects of the quantum mechanical model of atom. According to this model, electrons can only have specific values of energy, which means that the energy of electrons are quantized. The quantized energy values that result from the wave-like properties of electrons can be calculated along with the associated wave functions, psi, using the Schrödinger wave equation. The quantum mechanical model of atom supports the Heisenberg's uncertainty principle and says that one can only determine the probability of finding an electron at different points in the atom, but not its exact path. The atomic orbital for the electron is given by its orbital wave function psi. There are multiple atomic orbitals in an atom, as an electron can have many wave functions, each of which contains a maximum of 2 electrons. In a multi-electron atom, the electrons are filled in various orbitals in the order of increasing energy. Note that these orbits are two-dimensional circular paths around the nucleus, in which the electrons revolve, whereas atomic orbitals are three-dimensional regions around the nucleus where the probability of finding an electron is the maximum. Now let us see how the atomic orbitals are distinguished by quantum numbers. On solving Schrödinger wave equation for hydrogen atom, the solution gives quantized energy states and the wave functions which are characterized by a set of 3 quantum numbers, which are the principal quantum number, the azimuthal quantum number, and the magnetic quantum number. An atomic orbital of an atom is characterized by these 3 set of quantum numbers. Orbitals are distinguished from each other on the basis of shape, size, and orientation. The probability of finding an electron depends on these 3 distinguishing characteristics. Such orbitals are again distinguished by 3 quantum numbers, which are, again, the principal quantum number, the azimuthal quantum number, and the magnetic quantum number. A 4th quantum number, called the spin quantum number, was also introduced later to represent the spin of the electron about its axis. Spin quantum number is characteristic for an electron. Therefore, quantum numbers can be defined as a set of 4 numbers that provide the complete information about the electrons in an atom. Let's understand these quantum numbers in detail. The principal quantum number, denoted by the letter n, determines the size and, to a large extent, the energy of the orbital in which the electron resides. The size of an orbital increases with the increase in n. In other words, the larger the value of n, the greater is the distance of the electron from the nucleus. An electron needs energy to move to the higher energy levels as it has to overcome the forces of attraction from the nucleus. Hence, the energy of an orbital increases with the increase in n. Note that, for hydrogen and hydrogen-like species, energy as well as the size of an orbital depends only on n. In addition, with the increase in the value of n, the number of allowed orbitals increases and are given by n square. Shells are denoted by the capital letters K, L, M, N, and so on for the values of n equal to 1, 2, 3, 4, and so on respectively. The number of electrons in a shell is given by 2n square. Therefore, for n equal to 1, there will be 2 electrons in the K shell, and for n equal to 2, there will be 8 electrons in the L shell. The number of electrons in M and N shells will be 18 and 32 respectively. As the energy increases with the increase in n, the energies of the various shells follow the sequence K less than L less than M less than N less than, and so on. Let us move on to the next quantum number, that is, the azimuthal quantum number. It is denoted by the letter L. The number of subshells is given by the azimuthal quantum number. The azimuthal quantum number is also known as the orbital angular momentum or subsidiary quantum number. The azimuthal quantum number also describes the three-dimensional shapes of orbitals that you will learn about in the next module. For a given value of the principal quantum number n, the azimuthal quantum number L can have n values ranging from 0 to n-1. The value of L, in turn, defines the number of subshells, which means that when n is equal to 1, L is equal to 0. That is, there is only one subshell in first main energy level. Similarly, for n is equal to 2, L is equal to 0 and 1. That is, there are two subshells in second main energy level. And for n is equal to 3, L is equal to 0, 1, 2. That is, there are three subshells in third main energy level. Subshells corresponding to different values of L, that is, 0, 1, 2, 3, 4, are represented by the symbols S, P, D, F, G, and so on. The first four notations are the initial letters of the words sharp, principal, diffused, and fundamental, the words formerly used to describe different spectral lines. Thus, the subshells in the K shell for n is equal to 1 is S. In the L shell with n is equal to 2 are S, P. In the M shell for n is equal to 3 are S, P, D. In the N shell for n is equal to 4 are S, P, D, F, and so on. The S subshell has the lowest energy, and the energies of the subshells within the same principal shell follow the order S less than P less than D less than F. An electron moving in a subshell generates an electric field and magnetic field resulting from its motion around the nucleus. Thus, under the influence of an external magnetic field, the electrons moving in the subshells tend to reorient themselves into the specific orbitals. The number of preferred orientations of electrons belonging to a subshell is given by another quantum number called the magnetic orbital quantum number ML. Each orientation corresponds to an orbital. Therefore, magnetic quantum number helps to determine the number of orbitals within each subshell. For a subshell, there can be a maximum of 2l plus 1 preferred orientations or orbitals with values ranging from -l to +l, including 0. Hence, for L is equal to 0, the number of preferred orientations is equal to 1. Thus, S subshell can have only one orientation in space and only one orbital. For L is equal to 1, the P subshell can have a maximum of 3 orbitals with orientations along the 3 axes. Similarly, for L is equal to 2, D subshell has 5 preferred orientations and hence 5 orbitals. Using the same calculation, F, G and H subshells can have 7, 9 and 11 orbitals each. Note that all orbitals belonging to a subshell have the same energies and therefore are called degenerate orbitals. Thus, the 3 quantum numbers can very well define the energy, shape and orientation of atomic orbitals. However, these quantum numbers fail to explain the presence of closely spaced lines, doublets or triplets in the atomic spectra of multi-electron atoms. To explain these lines, in the year 1925, George O. Len Beck and Samuel Goudsmit introduced the 4th quantum number called the electron spin quantum number or MS. The two scientists suggested that just like the planet Earth, an electron rotates around its own axis while revolving around the nucleus. The electron spin results in an intrinsic spin angular momentum that can have 2 possible orientations, clockwise or anti-clockwise, relative to the chosen axis. These orientations are defined by the spin quantum number ms that can take the values of +1/2 and -1/2. These values are represented by upward and downward arrows and are called spin up and spin down respectively. The 2 electrons belonging to a particular orbital always have opposite spins.